right? Yeah, so exercise 20.1. Let's see, 7 and 10. Third second means t equal to 2 to t equal to 3, right? So let's see this question. A particle moves in a straight line so that at time t seconds after leaving a fixed point O, its velocity v meter per second is given by v equals to that formula. Find part 1, an expression for the displacement of the particle from 0. So displacement means you're looking for s, then to go from v back to s, you have to integrate, right? Because they start you off with velocity. So you just integrate this and you end up with the same thing, but with an extra t. Hold. Yep, that's correct. Yes, because this is just a constant plus c. Then by default here, you can just assume that you have to assume t equal to 0, then the s equal to 0. Because it starts from fixed point O. Then you sub this in, you can solve for c. And sub it in and you get s. Okay? Part 1 is easy. Part 2, displacement at t equal to 5. Also not that bad. Just sub in t equal to 5 and you end up with this. Okay. 8 times 5 is 40. How about, oh, is that at the end of question 7? Okay. Let me just double check. Question, oh, like, yeah, oh, that's it for question 7. Okay, easy. Then question 10. A particle P moves in a straight line so that its distance s meters from a fixed point O is given by s equals to 18t squared minus t power 4. T seconds is time after leaving point O. Calculate part 1, non-zero value of s when P comes instantaneously to rest. So that means v equal to 0. So you are given s, you want to find, you know that you have v equal to 0. So that means you want to go from s towards v. So you differentiate, right? So you differentiate and let's see what you get. When you differentiate as, let's see, this guy, you get 18 times of derivative of t squared, which is 2t. 18 times 2t, 36t. Good. Differentiate negative t power 4, you get, something wrong. What's wrong? Negative factor of first, 4t cubed, missing a 4. Okay, so error carry forward, let's see, 36 minus 4t squared. So there are 2 more roots, actually, t equal to 0 or 36 minus 4t squared equals 0. You could actually, you know what, let's just factorize it a bit more before we solve. So t times 36 is 6 square, 4t square is actually bracket 2t square, like this. A square minus b square, right? Will give you a minus b, a plus b times a plus b. Then this becomes 6 minus 2t, 6 plus 2t. Okay. Yeah, then from there you can solve t equals 0 or 6 minus 2t equals 0, which gives you t equals to 3, t equals negative 3. Which one you reject? You reject negative 3. That's an error carry forward. Here, what did they want? Let's read the question again. The non-zero value of s when P comes instantaneously to rest. Non-zero value of s. So you can assume that when t equals 0, don't need to assume. Sub in t equals 0, you realize s equal to 0. So they are asking for non-zero value of s, which means they don't want t equal to 0. That's why you reject, because s equal to 0 when t equal to 0. So to prevent s equal to 0, you also prevent t equal to 0. Okay, so to prevent t equal to 0, it basically means you reject t equal to 0. Okay, this part is fine. But the other 2 roots are wrong, should be positive 3, negative 3. And of course, negative is impossible. You can't have negative time. So you reject as well. So the only answer is t equal to 3. Ken? Right. Yeah, so that's not enough because they're asking for the value of s, non-zero value of s. So what you do next is sub t equal to 3 into the s formula. So s equals to 18 times 3 square minus 3 power 4. So 3 square, okay, I need a calculator for this. Let me see. I show screen. Okay, like this. Right, and 18 times 3 square minus away 3 to the power of 4. So we get 81. Okay? Okay, good. Let me just change back. Okay, good. So s equals 81. Next, we move on to part 2. The distance traveled by P in the third second. So hopefully you understood the hint. Third second means you want to look at the distance traveled from t equal to 2 to t equals to 3 duration. All right. So what's the procedure again when you want to find distance? 4-step procedure.
You find the points where v equals to 0.
Okay. The t values. Then what do you do with those t values?
Yeah, you sub them into the for S for displacement.
Yeah, into the displacement formula. So that means that you may need an intermediate step sometimes. Like if you are not given the S directly, you have to find S. Okay. Right. If you're given velocity, find S, you integrate. That kind of thing. Right. Then what do you do next?
Find for the time that they like want, like the
from t equal to
yeah,
t equal to a to n, let's say. Then you
Yeah.
have to also sub in.
to S.
Maybe I should label this as the desired duration. Questions desired period. Yeah. Then you can sub those t values. T equal to n to s. So now that you have all these different t values, all these different s values, what do you do? Step 4. Draw the
graph.
this one, snake diagram. Like to call it the snake. Draw a graph. Not exactly a graph, it's more like a diagram. Graph will have a y-axis, x-axis. This one doesn't. Yeah, so anyways, let's do that now. So do we have v equal to 0? Not yet, right? So let me see the working first. Sub t equal to 3. How come you sub t equal to 3? Interesting. Correct.
Cause third second. Wait, I think cause third second. Like it's not cause.
Oh no. Hey, distance is different from displacement. Okay, this one what you just found was but incomplete. This is only the intermediate step to find the displacement. Displacement is not equivalent to distance. Okay.
No, I think it's cause like cause like I solve here, then like okay, this is wrong, but like cause v is 0, then I see that v is only 0 when t is 6.
Oh wait, v equals 0 here. Right.
Yeah, I mean, cause
yes.
I thought that v equals 0 and t is 6. So then I just thought like it doesn't how to say. I thought like it doesn't change direction until t is 6. No. But I mean my thing is wrong
right.
lah. But like because
Yes.
of my thing is wrong, you know what I mean?
Yeah.
Like,
But
yeah.
even if that's the case, right? This just substituting t equal to 3 and then concluding s equal to a1 and that 81 you take as the distance is still wrong.
Oh.
Why? Because if it was actually 0, 6, and -6, okay, ignore the -6. What it means is the particle, let's say it moves to the right first and then it turns around like this. So this one t equals 0, that point is t equal to 6. Then you're saying, oh, t equal to 3 must be somewhere in between here, right?
Yeah.
Then you stub in this, you get a s equal 81. This 81 is, if this is 0.0, what it means is this distance here is 81. Is that the distance traveled in the third second? No, third second means you have to have another
From
t
t
equals to 2.
equals to 2.
And then you get a corresponding s distance from the origin fixed point. Then from there you have to subtract the 2 s values. That's how you get the distance in the third second.
Okay.
Make sense?
Yeah.
Okay, but actually this diagram is not correct because t equals 6 is wrong. So let me just remove this diagram. In case you're confused, let's do the correct one. So yeah, v equal to 0, we end up with t equals to 0, t equals to 3, right? And what is the desired time they want? They want, the question from part 2, what they want is distance traveled from t equals to t equals to 2 to t equals to 3, third second. First second will be from t equal to what to what? First second, if they ask first second.
T equals, wait, first second.
First second. T equals 0 to T equals to 1.
Okay.
Let me write this down. T equals 0 to T equals to 1. This is first second. So this is like English comprehension already. Then T equals to 1 to T equals to 2. That's second. How what? Second. Yes, second. Okay, I better not write the first in IRS, write the short form. First second. The second. Then this T equal to 2 to 3 is the third second. Okay, I don't write third. I won't spell it, I'll just write the short form. Third second. Okay, clear enough? Yes, okay, now let's calculate the S values. So what was my S value? Let's see. When T equals to 0, my S equals to 0. T equals to 3, my S equals to, what was my formula for S again? Let me double check. 18T squared minus T power 4. So when T equals to 3, what does this give me? 18 bracket 3 squared minus 3 power 4. Did we calculate this before? I think we did. Yeah, it's over there. It's 81. Okay, so we get a 81. Anything else we need to sub in?
T equals to 2.
2, because we want 2 to 3. Okay, this is like your A, that's your N. Sub in A, T equal A, T equal N. Okay, anyways, you get an S value, which is 18 times this square minus this power 4. Calculate and let's see.
3 times 18.
18 times, I don't know, just use calculator. 56. Okay, now that we have all these values, we can draw the snake diagram. So recap on the procedure. This is step 1. V equals 0, then from there you solve for the 2 T values, or that could be multiple. Then step 2 is to sub in those T values, get the corresponding S values. Then step 3 is to identify the A and the N, the starting time, ending time, and then you sub in whatever other T values is required to get the corresponding S. Now step 4, you want to draw the snake diagram. So I like to start off by, the only thing that's relevant is step 2, step 3. So I like to start off by drawing a distance line. Okay, then maybe I'll call this the fixed point O. Then what happens when T equals 0, you're at S equals 0. So S equals 0, so you're at the origin, fixed point. Then when T equals 3, it goes to 81. We can also quickly check out that as T increases from T equals to 0, the handwriting is so bad. I hope you can see. Is it clear enough? As T increases from T equals 0 to T equals 3, the S is also increasing. Do you believe me? If you don't believe me, let me convince you. Desmos, just draw the graph. Let me just set up the graph over here. Can you see the Desmos screen? Can? Yeah, so we're gonna draw y equals to 18t squared minus t cubed, right? The Desmos can only accept x and y, so I have to rewrite it. Capital epsilon is on. Sorry. Little y equals to 18x power 2 minus x power 4, instead of s and t. Okay, so this is how the graph looks. Let me zoom out. Okay, it looks like an M shape. Maybe I change the scale to make it look nicer. So y-axis could be, let's say, negative 1000 to positive 1000. Okay, it looks like an M shape. Can you see? Ken, are you convinced now that from t equals to 0 to t equals 3 is increasing?
I was always convinced.
Okay, very good. So anyways, when it's always increasing, right, what does it mean? It means that, I shouldn't use t, I should be using x. What this means is that it is moving in a single direction. Okay, moving in a single direction, it didn't change. When does it change? Only after t equals to 3. Then it goes down, right? When it goes down, it means that you're changing direction. That's why you call this a turning point. Like a roller coaster, you go up and then you go down. Okay, turning point. Okay. Now let's go back to the But you don't need this graph. You really don't need this graph. You can also check that it's increasing by simply, how do you check that our function is increasing? Don't review the answer.
Second.
Increasing. No.
Wait.
How do you check that s is just increasing from t equal to 0 to 3? To verify that our function is increasing, you take the what derivative?
Second derivative.
No, increasing function first. And you check that the value is
more than
positive.
0.
Okay. Remember dy by dx, if it's more than 0, increasing function. Okay. For its corresponding interval of values of x. If it's the other way around, you dy by dx less than 0, then it will be a decreasing function. So let's just quickly check that since I'm already here. So if you differentiate s with respect to t at first derivative, you realize that's just the velocity. What is this? It's just 36t minus 1, minus 4t cubed. Then all you need to do is to sub in t equal to 0 to t equal to 3, and you realize that, this value is always positive. Can? Okay, sub these in and you realize v is always more than 0. If v is more than 0, which is the first derivative of t, first derivative of s, that means that s is an increasing function from t equals 0 to 3. Anyways, all that means is that you can just move in one straight line. Okay, until you hit this point here when t equals to 3. This one is t equals to 0. And then you continue moving in the other direction. Is there another turning point? No, I don't have only 0 and 3. So that means you just continue all the way to the left. Let's see. All right. So let's label some relevant parts of the diagram. This part here, oops, just draw a double arrow. It's 81 meters. Right, 81 here. Then t equals 0, s equals 0. So it's just at the beginning, nothing to label. T equal to 2, where's t equal to 2? Must be somewhere over here, the particle. Then we can draw a vertical line down. What's the displacement? S equals to 56, right? So that means the distance over here is 56 meters. Can you see that? Okay, very good. So therefore, what's the distance traveled? This part here, from in the third second. So it's just 81
minus 56,
which is 21 plus 4, 25 meters, right? Okay. Is that okay? Very good. That's the answer. Okay, next. That's it. Is that I only tried 2 questions?
Yeah.
Okay, very good. Then we continue going through the rest. 11, 13, 16, 17, 31. Let's go through. Okay, wait. I'll just add on to this worksheet then. Question 11, is it? I hope you can see my shared screen now.
Yeah, I can.
Let me know if you cannot see. I am copying over the question. Okay, let's take a look at question 11. So the height h meters of a stone t seconds after it has been thrown vertically upwards from the ground level is given by h equals to blah. Find its velocity after 3 seconds. Find the maximum height reached and find the time of flight. Before it means you go up and then you go down. What's the time taken? Okay, so here h is really just the same as displacement. Is that clear to you? Right? So that means if we have h equals to 24t minus 3t squared, we can find the velocity, which is the derivative of the height, which will be 24 minus, square. 3 times 2, 6t. Good. Wow, what are you writing with?
I'm using the MacBook.
Oh, okay. Okay, clear enough. That's good. Then what did they say? Find its velocity after 3 seconds. So
Sub-3.
Yes, very good. Okay, so
18.
for part 1. Yes.
Maximum height reach. Sub v equals 0.
Yes.
Then t equals to 4.
Let's see. 6 t divided by 6 t equal to 4. Correct. Good. Then what do you do next?
Sub
Maximum height.
Sub t equal 4 into h equals 24t minus 3t squared.
Times 4 minus 3 times 4 square. So h equals to this. Right?
Then that's the answer.
Yeah. So let me just quickly calculate this. 24 times 4. Oops, where did it go? 24 times 4 minus away 3 times 4 power 2, which is 48. This one don't need to verify the nature. Okay, it is a maximum. It is a maximum. You can also quickly check. This one is a quadratic curve, right? Negative coefficient, so it must be a set face. So confirm must have a maximum. Make sense?
Mm-hmm.
Yeah. Okay. Roughly, yeah, roughly. This one, the graph not accurate. Okay, a little bit more accurate. It looks like this. It must intersect the origin. T equals 0 is one of the roots. But okay, that's not the main point. But let's move on to part. So let's move on to the part 3 now. The time of flight. Oh, actually might be relevant now.
From is asking from t equals 0 to t equals 4. Wait, I understand. The time is asking for until it comes back to
the ground.
h equals 0.
Yes.
Oh yeah.
So in other words, it's actually asking for this distance here. Can you see? When it goes up and then it comes back down. Can you see?
Oh, okay.
That pink color region is the time taken. So all you need to do actually is to just set h equal to 0 and solve for the roots. That's it. So let's see. This becomes 24 minus t squared. No, minus 3t. You can divide by 3. So this becomes 8 minus t equals 0. Therefore t equals 0 or t equals 8. Those are our two roots. 0. Very messy. Let me label with a 0 and an 8. T axis, h axis. Okay. So therefore the duration is actually just 8 seconds.
8.
Okay.
Mm-hmm.
Good. Next question. What's the next question I assigned? 13. Okay, let's take a look at 13. Distance question. New page. 13. A particle moves in a straight line. Wait a minute. Let me just carry this down. Okay, a particle moves in a straight line with its velocity v meter per second given by that formula, where t seconds is the time taken since leaving the origin O. When t equals to 0, its displacement from O is 3 meters. Fine, part 1. The value of t when the particle is at rest and the displacement at this instant. So straight away at rest, what does it mean?
V equals 0.
V equals 0. Okay, so let's do that first. So let me copy the formula first. So we write down at rest, v equals to 0. So 2t squared minus 3t minus 2 equals to 0. Can I factorize this? Let me see. Just use a calculator for efficiency. 2 minus 3 minus 2, I get t equals to 2 or t equals to negative half. This one clearly you reject. So t equal to 2 only. Okay? So value of t when the particle is at rest. Okay, that's the first part. This question very greedy. They ask me for two different things. And okay, very good. The displacement. So let's find the displacement now. S equals to integral v dt, which means you integrate
for
blah 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 blah.
T 2 over 3 t cubed.
Good.
Minus 3 over 2 t squared.
Over 2t squared. Yes, correct.
Minus 2t plus c.
Okay, good.
Then sub in t equals 0, s equals to 3.
No longer s equals to 0. Finally, we get to see a question where s is not 0. Okay, so what we do now is to sub that in. So
c equals to 3.
Yeah, just be careful. You must really sub in because in the future the question may not be so easy. The c may not just simply be 3, but usually it is usually. for polynomials. And therefore S equals to, I'll just copy the formula and replace the C with a
3.
Good. So now we have S equals formula and the displacement
So
at this
T
instant.
equals to 2 into
Yes, so
that.
this one, let me just read this first. And the displacement at this instant. Okay, so over here, you sub T equals to 2. Yes. So S equals to, let's see. I'll just write the working. Could you help me to type in the calculator?
Yeah. I can.
Is it -5/3?
Wait, what? I get something different.
Oh no.
Wait. Oh, okay, I know why. Oh yeah, -5/3.
-5/3. So how come got negative? Can have negative?
Yeah.
I need to can because displacement can be negative. It just simply means that you are starting from a point O and you're moving towards the left somehow at T equals to 2. Your -5/3 meters relative to the fixed point O. Yeah, to the left of point O. Can? Very good. Let's go on. Yeah. Next, part 2. The displacement when T equals to 3 and the total distance traveled by the particle in the first 3 seconds. So first 3 seconds is really just saying T equals to what to what?
T
0
equals
to
0 to T equals to 3.
Can you just sub in T equal to 3 into the S formula and call it a day?
No.
When it asks for distance? Not so
No,
simple.
because when T equals to 2 is a turning point.
It's a turning point. So it will sort of undo the displacement and then you go back like this. Anyways, let's just follow the 4-step procedure. Let me copy the question so I don't need to keep scrolling up and down. Like this. So displacement when T equal to 3. Okay, so when V equal to 0, let's just follow the procedure. When V equal to 0, we have to solve for T. Did we do that already?
2.
Yes, we got T equal to 2, turning point. So then when T equal to 2, we sub this into the S formula. So did we do that already? Yes, -5/3. What else do we need to sub in? The starting?
Sub in when T equals to 3.
T equal to 3. Okay. S equals to, let's see. Everywhere there was a T replaced with a 3. I'm referencing to this formula over at the top here. So what is it? -2 times, let me see. 3 plus 3. Okay. What is this? Three over 2 meters positive. Okay. One more missing one, which is
T equals 0, S equals to 3. I mean, yeah, T equals 0, S equals 3.
Yeah, that was given by the question, I think. Let me just double confirm, is it 3? When T equals 0, displacement equals 3. Okay, good. Yes, so T equals 0, S equals 3. Now we can draw our snake diagram. This is part 2. I should label the question. Okay, let's go. So line fixed point O, draw a broken line like this. Then where do you start off when T equals 0?
3.
Very good. So positive 3 meters to the right. So maybe draw a diagram like this, then label here positive 3, and draw another vertical line like this. Then I plot a point here, here. This is the direction you're traveling. So sorry, you didn't travel that. You're starting at that position. Sorry, starting over here. This is when T equals to 0. Then you move towards the left or right? Left or right? From T equals 0 to T equals
towards the left.
Towards the left. So eventually you hit -5/3 distance. So maybe somewhere here, -5/3. So you move this way. Okay, this is t equals to 2. And then you continue going straight all the way. Okay, when t equal to 3, what happens? T equal to 3, s equals to 3/2. So 3/2 is less than 3, right? It's 1.5. So that means it's somewhere over here. The distance, oops, maybe I'll label here 1.5. So the point must be somewhere here. This is when t equals to 3. Okay, is it clear so far? Okay, now we have to measure the distance traveled by the particle in the first 3 seconds. So from t equals to 0 all the way until t equals to 3. So what's the distance? Let's calculate. Yellow color part is how much? 3 plus positive 5/3. It cannot be negative, right? This part here. Then what's the blue part?
Is
This part here.
1.5 minus 5/3, which is plus 5/3.
Yeah, so just 5/3 plus 1.5. Oh, just use the diagram, right? This part is 5/3, this part is 1.5. Okay? Okay, good. So let's see, calculate. What do you get? 3 plus 5/3 plus 5/3 plus 1.5. And you get 47/6. Okay, so let's just write this down in decimals. 7.8333333 all the way. Okay. Now this is the usual technique to find distance, but there is an alternative technique you may eventually learn in university, which is that distance from t equals to 0 to t equals to 3. I didn't introduce this before. It's actually just the integral of the modulus of v from t equals to 0 to 3. Do you believe me? Let's do it now. Let's check. This is modulus. Let's copy the v function. So v equals to 2t squared minus 3t minus 2, right? Then let's draw the graph of this guy. Factorize this. What was it again? 2 minus 3 minus 2. I get t minus 2. I get a 2t plus 1. So that means I will have a graph that looks something like a positive coefficient, so happy face. The two roots are -½ and +2. When t equals to 0, where is it? Must be somewhere over here, right? So that's my y-axis or v-axis. That's my t-axis. Let's make it a little bit more accurate. Somewhere like this. Let's try and figure out what's the y-coordinate at that point when t equals 0. So when t equals to 0, v equals to, let's see, -2. Okay? Clear so far? So how do we deal with an integral of a modulus function? This one is also only in H2 max syllables. But let me just teach it to you. So basically, all you need to do is to first, step 1, draw the graph of the modulus fx. And particularly part 1, you must label the part that is the original function fx because it's already positive. Part 2 is to label the part of the graph which is actually negative. What do I mean by this part 1 and part 2? So if you want to draw modulus fx, right, this currently is v equals to 2t squared minus 3t minus 2. What I really want is to draw the graph of modulus of v. So in other words, I want, okay, maybe, you know what, maybe I'll just label this as y. What I really need is the modulus of v, which is the modulus of 2t squared minus 3t minus 2. Right? But this guy, it will actually be equal to 2 pieces. It's the original function itself. If the 2t squared minus 3t minus 2 is positive. Does that make sense? If the expression itself is positive, then modulus it, then nothing happens to it. It stays the same. Alternatively, what if it's not positive? It's less than 0 or equal? Okay, let's ignore the equal first. Let's ignore the equal first. Then you just have to times a -1 to it to make it positive. Does that make sense?
Yeah.
You times a -1 to make it positive. So let's take a look at the graph now. Here, essentially, when you say you take modulus, right, it just means the parts which are below the x-axis, this part here, you have to reflect it on top. So it goes like this. Let me think. Where's the line of symmetry? Negative b over 2a. So it's negative of b over 2 times of a, which is positive 3 over 4. So it's probably somewhere here. Okay, line of symmetry. Symmetry. Okay, can. Then this new graph that I've just drawn is the modulus of v function. So which part of it is relevant to us? It's only the part that is more than 0, when t is more than 0. So it's really just this part here, the blue one, and that part there, the green one. Can you tell that the 2t squared minus 3t minus 2 is the green one? And this negative of bracket 2t squared minus 3t minus 2 is, maybe I should use purple, is this part here. Oops, is this part here. Okay, let's just highlight the relevant ones. Can you see? Actually, the purple graph, negative bracket 2t squared minus 3t minus 2 extends all the way down. But I only highlight the relevant parts when t is more than 0 or equal to 0. Is that okay so far? Likewise, for the green graph, is actually the whole curve here. But I only highlight the part that's relevant, which is the right side, when t is more than 0 and is positive. Okay, so let's see. What does this mean now? That means that if we want to integrate this modulus of v, it's really just integrating two pieces. Can you see that there are two pieces? One piece here and another piece there, right? So when t equal to 3, let's just label, this is 2. Where is my t equal to 3? It's somewhere here. When t equal to 3, my y coordinate is 3 comma, let's see, 2 times 3 square. 2 times 3 square minus 3 times 3 minus 2, which is a positive 7. Now this 7 is irrelevant. I just wanted to plot the point to let you know that the graph stops there. Okay, but after I plotted it, I can now shade in two pieces of the graph. Can you see there's one piece on the left here and another piece on the right there? Pink color region and red color region. Can you see? Left side, right side.
Yeah.
Can yeah, those are the two regions that we are going to find the area of, and that area will give you the distance traveled. Let me show you. So this first this first pink color region, can you tell me what's the integral? Integrate what function? Upper minus
negative 2t.
Negative bracket 2t square minus 3t minus 2. From where to where?
From t equals to -2.
Wrong. No. Here, the limits, you see, this is dt. Then that means that the upper and lower limits should be t equals something and t equals something. T equals something is actually a vertical line. So it's over here, which is t equals to 0, and until here, right? Which is t equals to what?
2.
T equals to 2. Okay, good. Maybe I just draw a quick sketch of the diagram. So it's, and what I want is here to here. Oh, I should use pink color to be consistent. Let me try and do that. T equals 0 to t equals 2, this part here. Okay, good. Next one, we try to integrate the red color region, which is what function this time?
2t squared minus 3t minus 2t.
Okay, t equals to what to what?
T equals to 2 to t equals to 3.
2 to 3, and let me just draw a quick sketch but this time we want, ayo, not nice, not symmetrical. Like this. This time we want t equals to one red color. T equals to 2 to t equals to 3. That region there. Okay. Now we integrate. Let's do it. So factor out. Let's just integrate 2t squared minus 3t plus 2 first. This gives us what is this? Hold on a second. Let me think. Hold on. Wait a minute. If you integrate v, you're just getting s, right? We already did it before. It's over here. Right? Integrate v. Okay, so let's just copy that. And we also got c equal to 3. Okay, but that's not important. Just copy down the generic integral without the c. Why? Because we're dealing with definite integrals now. So it doesn't matter. It doesn't matter to have the c or not. After you sub in the upper and lower limits, they will just cancel away. So this is that integral. Then you can bracket, sub in 3, 2. But for the other guy, because there's an extra negative sign in front, you can factor it out first. So I'm going to factor out that -1 first. Then multiply by, still do the same thing. But the upper and lower is not 3, 2. It's, what is it? Oh, t equals 2, 0, right? Okay. Let me try and resize this and fit it nicely so it looks good. Okay, like this. Good. So, all right. So let's just do a clever trick here. Let f of t, or actually, you know what? There's an actual name for this function. It's called s of t equals to this fellow here. So what we're doing is really just -1 multiplied by s of t, but you sub in upper t equal to 2, lower limit t equals 0, plus that same guy s of t, but upper limit t equal to 3, lower limit t equal to 2. Does this look familiar to you? I tried this trick before when we were first dealing with the integrals, definite integrals, with all the a, b, and c, no actual values. So what you do now is you sub in s2, s0, and plus, next one, s3 minus s2. Can?
Okay.
Right, then now let's open up the bracket. -1 times in. What do you get? Negative s of 2. Negative gives you positive s of 0 plus s3 minus s2. Can? So minus s2 gives you -2 copies of s2. So -2 times of s2 plus s0 plus s3. Can, this is just because I'm lazy. I don't want to keep on writing this whole thing, but replacing the t with 2s, with 0s, with 3s, with 2s. Very lazy, very troublesome. So I try to simplify as much as I can. And finally, now really no choice. Then I substitute. The t in with whatever value it is into the s of t. So what we get? -2 times of bracket s of 2. So everywhere there was a t replaced with 2. Can you help me to type this in the calculator as I write? Plus s of 0.
Yeah.
This becomes 0 minus 0 minus 0. Plus s of 3. This is 2t cubed over 3 minus 3 times 3 squared over 2 minus 2 times 3. Yeah, type this in the calculator.
I get math error.
Math error.
I get 23 over. Wait. I messed up somewhere. I got 23/6.
Ah, yeah.
Wait.
3.7. Is it my handwriting?
Wait. Okay.
Oh, no. This is 2.
Okay. Yeah.
Let me know once you get 47/6.
I'm at 59/6.
Are you missing a bracket here, a times here, a negative sign? I don't know. Okay.
Oh, wait.
I wanted you to type this
Okay.
part here.
I get it.
Can 47/6 meters,
Yeah.
which is 7.83333 meters. What a coincidence. It is the same as what we got from doing the snake diagram. Whoa.
Not a coincidence.
Yeah, of course, it's not a coincidence. Okay, but this is what is usually taught in universities. They don't draw snake diagram. They draw integrate modulus of E. And to understand how to integrate this, you must learn how to integrate the modulus function, which is a bit of work, as I have demonstrated here. Okay. Oh, sorry, I didn't write down the instructions fully for how to integrate a modulus for the integrand. Draw y equals modulus fx. Part 1 label y equals fx. Part 2 label y equals negative fx, which is basically the green color and the purple color. This guy is fx. That guy is negative fx. Then from there, step 2, you split the integral at sharp point. What is sharp point? If you look carefully at the graph, you'll notice that there's one sharp point over here. Sharp point. So what we are doing is we're splitting the integral up into 2 pieces. T equals 0 to t equals 2, that's for the first piece. For like the sharp point is like a line here. Then t equals 0, t equals 2 is the left half. Then the second piece is t equals 2 to t equals 3. That's for the right half after the sharp point. Can you see that? This is before and after the sharp point. Understand? Can yeah, okay, that's it. That's our H2 topic already. Draw y equal modulus fx, label positive, label negative, split the integral at the sharp point. Okay, good. Done. So I showed you 2 different ways to find distance. This second way is not technically not in the H2 max. It's technically not in the A max syllables. It's only in H2 max. Actually, you know what? H2 max also don't really talk much about it. You only get to see this in uni. Or physics. Okay. Can understand? Let us move on then. What question? 11, 13, 16, 17, 21. 16 is where? 16 is over here. Let's take a look. 16. Still have 17, 21. Okay, let's take a look. Particle moving in a straight line passes a fixed point O on the line with its velocity 30 meters per second. So V equals to 30. Passes through fixed point, so T equals 0. The acceleration A meter per second square of the particle T seconds after passing O is given by A equals 13 minus 60. So A equals 13 minus 60. Recall that as VA, forward direction, differentiate. Meters becomes meter per second, becomes meter per second squared. Each time you differentiate, you're finding a gradient of a curve, which is a change in y over change in x. Change in y will be whatever is the quantity you're dealing with. Like let's say this is s and this is t. Then delta y over delta x. The units are, if you look at it, it's s in terms of meters, t in terms of seconds. So it will be meters over a second, right? Whereas if you change, let's say, this S into something else, let's say V meters, then, sorry, how can it be meters? Velocity is meters per second, the units. Then that means that your units for the change in Y over change in X will be meter per second over seconds, which makes sense. It's meters. Hold on, what am I saying? Oh my goodness, sorry. Which will give you meter per second over second, which is meter per second square. That gives you the acceleration, right? Sort of acceleration, right? When you differentiate the displacement just now, it was to get you velocity, but now when it's velocity, you differentiate, meaning you get the gradient of the tangent line, you get acceleration, meter per second square. Okay, but anyways, back to this one. We start off with acceleration instead. Now you want to calculate velocity. So how do you go from A back to V? Opposite of differentiate, which is
Integrate.
Integrate. So that means we get V equals to integral A of dt.
13t. 13t minus 3t squared.
Yeah, because of the dividing by 2
Plus
6 over
c.
Plus C, very good. Okay, then what else do we know?
When t equals 0, v equals to 30. So c equals to 30.
Give me a second to write this down. So 0 minus 0 plus C, and therefore C equals to 30. So therefore V equals to 13t minus 3t squared. Very good. That is part 1. How about part 2? The time taken to reach the maximum distance from O in the direction of the initial motion. Oh, sorry, I forgot to plus 30. Oops. So how do you determine the direction? Move left or
Positive
move
or
right?
negative?
Which quantity, S, V, or A?
S.
No.
Wait. What?
Negative. Actually, yeah, that actually works. Yeah, actually both works. S more than 0. Will tell you. But usually what we usually use is V. These cases will tell you it's at the right. Oh wait, sorry. No. The direction. No. Cannot be S more than 0. Sorry. You could be this situation. Let me show you. T equals to 0, T equals to 3, something like that. At this point here, T equals to 4, let's say. What's the S value? S equals to, let's say, 5 meters, positive. So S equals to 5, which is more than 0. But is it moving towards the right? The direction?
Mm-hmm.
No, right? It's not. Can you see? Okay, I use 6. If not, it confused with my S. Can you see that this at this point, when T equals to 4, it is not moving towards the right, it's moving towards the left, which means that our V is less than 0. Okay. Hi. Can you hear me?
Yeah.
Do you understand this concept? S cannot tell you the direction. V tells you the direction. S more than 0 is only telling you its distance from the fixed point O, which is a positive 6 meters towards the right. Its current location is towards the right, but it's not moving towards the right. Okay, we write this now. Location to the right of fixed point, but the motion is moving leftwards. The question here when you're asking for direction is what direction is it moving towards? Moving to the left or to the right? So the answer to this one is look at the SIGN sign, not the sine 30 degrees sign of V. V more than 0, moving to the right. V less than 0, moving to the left. Okay, anyways, how? So direction of the initial motion. Initial means what? T equals?
T equals 0.
0. Okay, so we're gonna sub in T equals to 0 into the V. And then we check the value of V. Oh, we realize it's 30, which is more than 0. So it's moving to the right, or rightwards. Okay? So if it's moving rightwards, right, that means that we want, let's read the question again. The time taken to reach the maximum distance from O in while you're moving rightwards. Right, this part here is really just saying while you're moving rightwards. Time taken to reach the maximum distance from O while moving rightwards. Okay? So how to find maximum distance from O? Distance from O. When they have a from, means it's a distance that also takes into account a fixed reference point. So this is not just a simple distance, it's actually known as displacement. So in other words, this question you can reinterpret as maximum displacement. Is that clear? The English comprehension? Okay, good. So they want the maximum distance, maximum displacement while moving rightwards. Time taken to reach the maximum, to achieve maximum displacement while moving rightwards. How do you do that? How do you get maximum displacement?
V equals 0.
Means you need to star differentiate equal to 0, solve, and table not required. The table is to determine the nature, but that's not required. Differentiate what? Differentiate S with respect to T, which is really just V. Then you equate to 0. Okay, so part 2, all they're asking you to do is to sub V equal to 0. Okay. So therefore we get 13t minus 3t squared plus 30 equals to 0. Let's rearrange it nicely. Okay, and from there, let's use calculator to solve. Sorry. Okay, sun times -1. I times out -1 already in my head. Okay, I show one extra line. So it's 3t squared minus 13t minus 30 equals 0. Then I factorize. Is that okay? And then from there, t equals 6, t equals -5/3. T cannot be negative, you reject this, t equals 6 only. So this is the t value when you have v equal to 0, maximum point. So maximum displacement. So what is the time taken? Answer is just 6. T equals 6 seconds. Actually, let me think. Yeah, that's it. That's t equals 6. There's no other way. Because there's only one turning point. Okay. Yeah. Maybe a quick sketch of this curve would be something like this. This is V against T. So what we'll have is y-intercept 30 to go up and goes down. This occurs at t equals 6, the maximum point. Okay? Okay, good. So they're asking how long does it take this time taken to reach the maximum point. Seconds. Good. That is part 2. Let's move on. Part 3 now. This maximum distance.
Maximum distance.
So it's a distance question.
Find when v is 0, we already have when v equals 0. The time that they want from
So let's
what
read the
time
question.
of-
This maximum distance. Calculate this maximum distance. So
I mean from t equals 0 to t equals to 6.
yes, that's it.
Then
So
wouldn't the answer just be you sub in 6?
yes,
As in you sub
yes,
in t equals 6 into s.
correct. Because this is before the very first turning point. So distance will just be, okay, hold on a second. Let me think of it. What is the original displacement? When t equals 0, what's the s value?
30. Wait, I
That's
mean,
v, that's v. Okay, if they didn't mention, we have to assume. We have to assume it's 0. Assume t equals 0, s equal to 0. Yeah, then if that's the case, then yes, you're correct. Actually, the distance is just s of 6. Right. Which means that we need to find s. How do you find s? You have to integrate v dt. Then later you sub in with t equals 6. So what does that mean? Let's see. Maybe we can do find the s first before we sub in t. So s of t equals to integrate v dt. So integrate v, what's v? It's over at the top here. Erase the v equals, you integrate dt. What do you get? 13
over 2 square t square minus t cube
over 3. 3 cancel.
plus 30t plus c.
Okay. But t equals 0, s equals 0.
Therefore, c equals to 0.
Okay, and therefore s is equals to
13t square over 2 plus t cube plus 30.
and then plus 0. Okay, good. Done. Okay, c equals 0. So if s equal to this guy, then finally distance, because at t equals 6, the displacement and distance happens to be exactly the same. You just need to sub in. It's before a turning point. Yeah. Oh, 6. Sorry. 6 power 3 plus 30 times 6. I'll leave you to type this in the calculator on your own. Okay. Okay, next. Let's go. 16 is done. Let's take a look at 1721. What's so special about these two? Advanced. What's so advanced about? Don't know. Wait, let me try and squeeze everything on the same page. Okay, let's look at 17. So a particle P travels in a straight line through a fixed point O. Its distance s meters from O is given by that formula. Let me copy it down first. Blah, blah, blah. Okay. Plus 40. And where t seconds is the time after motion has begun. Calculate part 1. The distances of P from O when its velocity is instantaneously at rest. Notice they use plural word here. So we've got two different distances. So instantaneously at rest, or sorry, at instantaneously 0.
V
Okay, here
equals
they are
0.
more. Yeah, they really tell you v equals 0, huh? So you have to first find the v. S to v, differentiate or integrate?
Differentiate.
Displacement to velocity, you want to differentiate. So you get 3t square minus 9 times 2, 18t plus 15. That's it. Okay, maybe I add one more line to remind ourselves we are differentiating s. Okay, then you just have to sub v equal to 0. So we end up with this guy equals to 0. From there, you solve for t. Let's see what it is. 3 minus 18 plus 15. You end up with t equals to 5 or t equals to 1. Right? So there are two different t values. We just make the small one on the left side, big one on the right side. Make it look nice. Like t equal to 1, t equal to 5. What do we want? We want distances of p from O when its velocity is blah. Okay, when t equal to 1, when t equal to 5, find distance of p from O. So because it's a distance question, we need to draw the snake diagram. Okay, this is not good enough. Okay, what's the 4 steps? Step 1 is here, sub v equal to 0. Step 2.
Step 2.
What do you do with those t values?
Sub those into S.
T equal to 1, S equals to, let's see, 1 minus 9 plus 15 plus 40. Let's calculate this. 1 minus 9 plus 15 plus 40. I get 47. Positive. How about t equals to 5?
I get
The S formula is on top here.
I get 15.
15, huh? Okay, very good. Then now we can draw a diagram. So let's see, snake diagram. Here's my fixed point O. T equals 0, t equals 1 become positive 47 should mean you move rightwards. And then after that, you turn. So maybe like this. So t equals to 1, t equals to 0, then t equals to 5. Why do I pick these 3 points as the t equals 0, 1, and 5? Because when t equals to 1, the displacement, how much? 47. Positive, right? Then when t equals to 5, displacement is how much? 15. Positive. Does this diagram make sense?
Mm-hmm.
Okay, yeah. Good. Then from there, what did they ask? Find the distance of p from O when its velocity is instantaneously at rest. Oh, sorry, this diagram doesn't make sense. Why? Because there's actually 2 different turning points. It shouldn't just go all the way to the left. What should it do? It should turn rightwards. Okay, can? Yeah, the diagram not very accurate, but you get the rough idea. You don't have to go and actually count this curvy distance. No, it's not drawn to scale. The particle is actually just moving to the right, then to the left, and then to the right again, along the same straight line. 1D kinematics. This snake diagram is just there to give you some sort of visualization that is moving left and right. Okay, good. So how?
How?
Actually, the answer is just 47 and 15, right? T equal to 0 to t equal to 1. What's the distance? 47.
47.
T equal to 0, t equal to 5. What's the distance?
15.
15. Okay, yeah, that's it. Okay, so for the special case where they're asking about distance of the turning points and those turning points itself, we don't need to do the snake diagram. Displacement is the same as distance in those special case, in this special case. Okay? But don't worry lah, huh? You see the word distance, just draw that diagram. Just draw this diagram. Follow the 4-step procedure. And then you stare at the diagram and realize, oh, actually, it's just 15, huh? Actually, it's just 47. Okay. Cool. Okay, never mind. But the general procedure of the 4-step procedure still works. Okay, let's look at part 2 now. Any questions for part 1? Mic test, can you hear?
No question.
No. Okay, let me know if you do. Then part 2. Calculate the values of t when the acceleration has a magnitude of 9 meters per second. A equals to 9. T equals question mark. How?
In differentiate v.
Yeah.
6t minus 18
Yes.
equals to 9. Sub a equal 9. So 27 over 6.
Divide by 3, you get 9 over 2, 4.5. Okay? Yeah, that's it. Values of t. Bad question. Bad English. Should be just value. Only one. Okay? Okay, very good. Next. What's this question? 17. Another one, 21. Let's see 21. What's so special about 21? Okay, there's just an extra question. When a particle is moving at its maximum speed, what is the acceleration of the particle?
When it's moving at maximum v. 0.
Gradient
0.
equals 0, so acceleration is just 0. That's it. Done. Oh, interesting. When you're moving the fastest, you're not accelerating. A equals 0. So, do you recall F equals ma?
Yeah.
A equals 0, what happens? F will become
0.
So when you are the fastest, you have no force. Weird or not?
Yeah.
Weird, huh? You are the fastest, but you have no force. Very, very interesting. Go and ask your physics teacher why is that the case. I cannot explain. What does it mean? I don't know. Just a formula. Okay. Anyways, yeah, that's it for kinematics. Is it? This is a summary, this one you already know. Differentiate to go forward, integrate to word by words. Right? Then for the study notes, this one I will leave you to read it on your own. Actually, I gave you more questions for set A and set B. I think you should try. You should try it on your own. Okay?
Okay.
Go and try. And since it's only 9:30, let's start a new topic. I told you I want to use the GC, right?
Yeah.
Okay, very good. Actually, there is an issue, which is that you are using the Mac version. So there's the issue of it doesn't have the apps. All that I actually wanted you to see is okay, you know what? Never mind. Still can. Let me just start a new lesson. Okay, things that are not in Amex. Ready?
Dude, right now my GC is not working.
Huh? The email not working?
Like it says LCD off. You wanna let me share my screen?
Yes.
So like, yeah.
Yes, please.
It says host disabled participant screen share.
Oh, wait. How do I I'll just make co-host. You should be able to share now, I think. Can you share?
Oh, yeah. Okay, yeah. Okay. So I got this. Yeah, and then it does this. Yeah. I don't know how you get the buttons and stuff.
go to docs. DOCK. Capture docs debug. Extra.
Capture.
At the top, C move file calculator capture docs debug. Top left. Top left. Top left.
Oh, okay.
Yeah.
Docs.
Okay. Keypad. Yeah.
Oh. Lol. Okay.
Press the on button.
Wait, what on button?
A
Oh, as
calculator
in
has
on
a
the. Oh, okay. Okay.
Maybe you should continue sharing screen to check.
No, I got it.
Is it on? Is it on? Okay,
Yes.
great. You know how to turn on a calculator. Great. Okay, let me share my screen as well. I'll show you this. Where is my C move? Let me find it. Hold on a sec. Can you see my calculator? Yeah, okay. So anyways, clear. Right. What we are gonna learn today is integration techniques. Okay, we're gonna learn integration techniques that are in H2 Max, but you didn't learn in AMAX because it's not in the syllabus. So in case you need it. So let me show you. If you press math, you can are you following while I click? Press the math button here.
Yeah.
Right, you can scroll up and down, you see, up and down. Then I want you to go to number 9 for function integration. FNINT means function integration. Click. What do you see? Oh, an integral. Right? Let's say we key in 0 here and go up. Are you following so far?
Yeah.
And then second, after you press the second, you'll see that the arrow changes to up. Okay. You click on this button here, which is beside the blue color pi. Click and you'll get a pi. Integrate from 0 to pi of, let's say, sine of, let's say, x. The variable here, can you see? I'm going a bit fast. Let me know if you are following. Okay, then you close the bracket. If you get sine x, then press the right button and press x. Then you press enter. Whoa. 2. What's that? Is the screen is it too small?
No.
No. Okay. If not, I could just I don't know, make it bigger. Could I? Can I? I can't. Okay. It's as big as it goes. Yeah. I hope you can see. Can see. Okay. So do you also get that result? Following so far? Okay.
Yeah.
You don't? Can or not? Let me know if
You go math, then 9, then
function integration 9. Then you can type in any type of integral you want, provided you give the limits. Okay. Let's say I go negative pi to positive. Wait, let me think. Is it pi? No. Let me think. Yeah, negative pi to positive pi of, let's say, cosine x is like cosine. Press the variable here. Can you see the variable button beside the alpha?
Yeah.
Click, close the bracket. Then press the right button and press the variable again. Enter. What's that? Wow, so complicated. What's that? You read this as negative 1.13 blah 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 times 10 to the power of negative 13. Okay. E minus 13 means times 10 to the power of negative 13, which is a very, very small number. Although it shows negative, actually this is a calculator error. It's actually equal to 0. Okay, this integral should exactly be equal to 0. So this brings up the one important point about a calculator, which is that it is not capable of calculating values sometimes, and will give you an estimation. In this case, it should have given you the exact value of 0, but it gave you decimals instead. Is it clear? So it's just a tool. You must be, as a user, you must be smart enough to detect this kind of situations where the calculator is giving you an estimation. actual answer should be 0. Okay.
Okay.
Okay, good. Next, let's go into integration techniques. So what are some of the things I wanted? Let me see. What do I want to teach you? Oh, sorry, integration. No, not integration. I want to teach differentiation first. If not, you can't do the rest. Let me share back my screen on the calculator. I showed you integration already, but I can also show you differentiation on the calculator. Let me press the clear button for clear. And go to math again. Then you can scroll up and down.
How do you backspace?
Backspace? Okay, let me just go up. What do you mean by backspace?
Like let's say you wanna like change cosine x from the previous one to like sine x.
Okay, can. Let's say you want to recycle a working, you can press the up button up until it's selecting one particular line. Let's say you select the previous one, sine x. You press enter this line after it's selected. Click. What happens? Oh, it appears. Then you can just click left. You can edit. You can even change to tangent. Ooh. Yeah, this one undefined. Cannot. Cosine. Cosine is good now. Oh, another bunch of decimals. Right, that's how you edit. But more importantly, now I want to show you. Go to math again. Scroll up and down until you hit n derivative. What do you think this stands for?
Derivative.
Exactly, derivative. Okay, so we're going to key in the variable x, and then let's say whatever function you want. Let's say you give it something simple about x to the power of 2. Do you see that? This one is power 2. X squared.
2 power.
Here, notice that these are only for definite integrals and also definite derivatives. Definite meaning you must sub in the x value. So here, if you differentiate x squared, what do you get? 2x, right? Sub in x equal to 3, then it'll be 2 times 3, which is 6. Let's see if it gives us the answer. Yay, it does. Wow, so smart, this calculator. Graphic calculator. Okay?
Yeah, okay, I get same.
Yeah, you get the idea already? Okay, good.
Yeah.
But this calculator is still limited because it is only able to do definite integral, definite derivative for single variable x. Now what I'm about to teach you is something more complicated that the calculator cannot handle. It's called implicit differentiation. Let's go. Okay, give me a moment to load the screen. So first one, I'm gonna teach you. Okay, sorry, not integration techniques. Cannot. Have to be differentiation first. So let's start with the classic question of you have a wall, and then you have a floor. Can you see the wall and the floor? My very artistic wall and floor.
Okay.
Can see, now we have a staircase. My very minimalistic staircase from our side view. Can you see my blue color staircase? Step ladder. The step ladder somehow the wall very oily. I think maybe it's a kitchen. The floor also very dangerous, very oily. Then it starts sliding down like this. So it slides down like this, and then it slides down a bit more like this, and then it slides down a bit more like this. Can you visualize what's going on? Can, right? But let's not draw so many lines. Let's just stick to a right-angled triangle like this, and let's label the lengths. This is y here to here. This is x here to here. Then let's say that the length of the ladder is 10 meters. Okay, right angle. Can you form an equation? What kind of equation? Right angle triangle. Come on.
5 times.
X squared plus y squared equal to 10 squared. Okay, so far. Now let's say this is a rate of change question. I tell you that the ladder is sliding down. Dy by dt is, let's say, I don't know, -1 meter per second. Okay, so it's sliding down at a rate of -1 meter per second. Question. Oh, wait, one more idea. Dy by dx, I must give you as well. Let's say, for example, wait, I can't give an exact value. If not, I might be wrong. Let's say that the dy by d, no, the dx by dt is some value a meters per second. Okay. Question, find. Okay, you know what? No. I shouldn't give all this. No. Don't need to give you anything else. The question is find dy by dx. How would you do it?
Okay. 100 minus x square equals to y square, square root both sides. Then you get y equals to square, yeah. Then
Which is power
if-
half.
dy over dx equals to half bracket open
What's in between the brackets?
100 minus x square
Power becomes
minus half
times.
and times 2 negative 2x.
Yes, negative 2x. Differentiate 100 minus x squared. That's the t, Okay, this is how you would do it based on what I taught you. 2 and 2 cancels away. You're left with negative x on top. Then negative half, you can bring it down, becomes positive half, which is really just a square root. 100 minus x squared. You can rationalize the denominator, but I'm not going to do that. So this is what you would get. This is the procedure you would do based on what I taught you. You make y the subject so far, right? Next, what I'm going to teach you is known as implicit differentiation. You can actually just differentiate this straight away. Let me show you. X squared, let me write the name of this topic. It's called implicit differentiation. So with implicit differentiation, you can solve this more quickly. So x squared plus y squared equals to 10 squared. Right? You can actually do the following. Differentiate with respect to x on the left side, differentiate with respect to x on the right side. Now, this is 10 squared, a constant. Differentiate with a constant, you just always get a 0, right? Okay. So how about this part here? Well, when you differentiate, you can differentiate term by term, right? So you can differentiate the first guy. So d by dx of x squared plus d by dx of y squared. Clear so far? Very good. Now this x and x match up. Okay, very nice. You can differentiate as per usual. This gives you 2x. Okay. Okay, following so far for this blue one? But this second half, something wrong. Differentiate. There's a y here. There's a x there. The variable don't match up. What did you learn from rate of change when the variable doesn't match up? What can you do? Make them match up, right? Like pretend that a equals to y squared. Then now we want to do, now essentially what we're doing is dA by dx. So what can we do?
0.
Split, right?
Oh, dA over dy.
You introduce your own dy. Okay, maybe I put in black color. Right? Then from there, dA by dy becomes what?
2y.
2y. Then times a dy.
2x.
Dy by dx, you cannot do anything. Leave it alone.
Okay.
Right? And remember what was our objective actually? Implicit differentiation. Sorry, did I not mention? I said that it's a shortcut to finding out the dy by dx.
Okay.
And dy by dx is right here. From the rate of change to the rule.
Make it the subject.
Make it the subject, exactly. And then you can carry on. So here, what you need to remember is differentiate the y square. You just have to, with respect to x, you just have to remember differentiate y square with respect to y first, then you get 2y. But you always have a
Always have a cat.
The cat has a dy by dx tail. Don't chop off the cat's tail, even though it looks a bit weird. Okay, even though it looks a bit weird, you must always have the tail here. This is the key idea in the implicit differentiation. When you're differentiating y with respect to x, it doesn't match up, but you still can differentiate. Just treat it as if it's differentiating with respect to y, you get 2y, but you must always bring along a tail. the dy by dx tail. The reason I've already shown you over here at the bottom. dA by dx, you treat A as this guy as A, then you take dA by dx, right? You reinterpret the question. dy squared by x by dx is the same as dA by dx. Then from there, you split it because of chain rule. Then from there, you can introduce your own letter you like, dy. Why do you pick dy? Because dA by dy means differentiate y squared with respect to y, which is just 2y. And dy by dx just tags along. Don't need this one, so slow. Just straight away remember the key idea. Differentiate y squared, get 2y, bring along a tail. Okay? Good, equals to 0. So actually, you can go from here to here in one line after enough practice. Can you see that? Right, let me just highlight. X squared becomes 2x. Y squared becomes 2y, but with an extra tail. Then constant, maybe I use a different color. Constant 10 squared becomes a 0. That's easy to do, right? With some practice. Okay, good. So from there, let's just rewrite it neatly first. From there, you can make dy by dx subject. How? 2y times dy by dx equals to positive 2x bring over become negative 2x. From there, dy by dx equals to negative 2x over 2y. 2 and 2 cancels away, negative x over y. But then you ask me, but you say you're gonna get the same answer, but it looks very different. Why? What's the difference? Maybe it will look a bit similar if I bring in the minus on top and make the fraction a bit longer.
Y equals to square root 100 minus x squared.
Yes, so therefore you can simply substitute the y with square root 100 minus x squared with a negative x on top. And you see, well, voila, is that the correct word? Voila, they are the same, okay? Can you see that? So this is your first, did I actually explain this before? I can't remember, but implicit differentiation, right? This is the key idea. Implicit differentiation is a shortcut to differentiating a lot of complicated expressions, okay? So let me show you more complicated examples. Let's say that we start off with something that you want to differentiate. For example, let me try and think of something that will make your life difficult. Let's say square root of sine x. This is enough to cause a lot of trouble. Here's how you do it traditionally. First step, maybe you rewrite this as, I don't know. Let me show you both ways. The traditional way, you already know how to differentiate all this. Now it's just teaching you a new technique to make things faster. Sin x power half, okay? Then differentiate. So you bring down the old power minus 1 to get the new power. What happens to the base? You differentiate sin x and write down cosine x here? Correct or wrong? In between the brackets.
Wrong.
Wrong. You must always copy down the base first.
Sin x and then outside cosine x.
Yes, this is the differentiate outer function. Then you multiply by the derivative of the inner function. The inner function in this case is sin x, differentiate inner, you get cosine x. Okay? Okay, actually not that bad, right? Not that bad. This is just a basic example. 2 times square root sin x. Okay? Now let me show you another way with our new technique, implicit differentiation. Here is what I would recommend my students to do. When you see square roots, be scared. Yuck, square root. So what you do instead is, before you differentiate, you square both sides. So let me just copy the equation first, and then I can nicely put in my bracket, bracket, power 2, bracket, bracket, power 2. Square root, square, cancel away, you're left with just a sin x. Right-hand side, left-hand side becomes y squared. Okay so far? Then now we apply differentiate with respect to x on both sides. So this one, if you differentiate y squared, what do you get? Pretend it's with respect to y. Do the same thing as per usual, right?
Yeah.
Power, what do you get? Let's say you
2y.
2y, yes. But don't forget, you must always have the
times dy dx.
dy by dx tail. That looks very familiar. Oh yeah, we just differentiated it just now, huh? Over here. Differentiate y squared, 2y times dy by dx. Do I need to explain this again?
No.
Tony, it's the same thing. Reverse the video and rewind the video and watch it again. So anyways, what we have is 2y times dy by dx on the left-hand side, but on the right side, differentiate sine x with respect to x, what do you get? Differentiate sine, you get
Cosine.
cosine x. From there, you can make dy by dx the subject. How? Cosine x over 2y. But wait a minute, what was y in the first place? Y is?
Square root sine x.
So you can just sub it in. So cos x on top, 2 times root sine x below. Done. Okay, arguably more steps. Arguably more steps.
Yeah.
Let me try and convince you that this is the correct way to do it. Let me find a complicated example. Give me a second. Where's my Maclaurin series? Hold on now. Hold on now. I need to convince you that this is the correct way to do it. Okay, wait. Right, of course, if I just make it in terms of y. Next example. What if I have, say, y equals to, no, let's just copy this. Dy by dx equals to 2 times square root of 1 plus y squared. This is the first time that you have ever seen an equation where the right-hand side contains a y. Whoa. It's not x. But you can still differentiate this. Now what I want you to go to find is d2y by dx squared. Second derivative.
Okay.
How? Very simple. How do you get d2y by dx squared? Just please remember that this is not equals to dy by dx power 2.
Okay.
Never equal. What is it actually equal to? How is it related to the first derivative? Yeah, it's the derivative of the first derivative. Okay. Differentiate the first derivative to get the second derivative as your answer. To obtain the second derivative as your answer. Okay, so anyways, you differentiate with respect to x of this expression 2 times square root, whatever. Then how? Oh no, you realize that this is in terms of y, but this is x. So you can think of it like this. This one is usual. Nobody ever does this when you're using implicit differentiation. Only when you are beginning, then you do this. So what I just asked you to do over here is essentially find dA by dx. Okay, I'm asking you to find dA by dx. But remember, chain rule allows you to split it into top left, bottom right for the dA and the dx respectively. But you introduce a good letter. Here, it's in terms of y, right? So what letter would you use? dy. Huh? Make sense so far?
Mm-hmm.
Now you have to differentiate this fella, which I can rewrite as 1 plus y squared power half with respect to y. How would you do that? dA by dy. Keep the coefficient 2. Differentiate whatever power half. What do you get? Bring down the old power half. Minus 1 to get the new power negative 1. What happens to the inside? In between the brackets.
But it's stay the same.
Stay the same first, and then
Differentiate
times,
the inside.
which will give you?
But then it's 2y.
2y. But wait, because it's in terms of y this time, yeah, it's perfectly fine. Because you see, here is with respect to y. Okay, so you don't need to include a tail. Sorry, no, don't include a tail. The tail is over here. dy by dx. Tail only appear one time. Sometimes depends on the question. Can? Do you see dA by dy is this entire expression? That's my A, that's my dA by dy. My y is my independent variable now. I hope you're not too confused. Can just pretend that y was x. Okay, just changing the letter. Instead of dA by dx, it's dA by dy because the letter is y. Okay, so far?
Okay.
Can 2.5 cancel away, you're left with 2y times all that. Let's just make it look nice. 2y on top, 1 plus y squared power positive half below, which is actually just the same as a square root. So I'll just rewrite as a square root, then times dy by dx. I hope you are not confused. Following?
Yeah.
Can so from now onwards, whenever you want to differentiate, let's say go back to here, differentiate this guy with which is in terms of y with respect to a different letter x. All you need to do is to pretend that this is the this y, treat it as if it's an x and differentiate as per usual. But we use the letter y instead of x, which gives you back to 2y over square root 1 plus y squared. But you must always bring in the dy by dx tail at the end of the day. Is it clear? So this is the answer. Bam, over here. There we go. Okay, done. But it's perfect. But then you realize, hey, how come got dy by dx when we are finding second derivative? That's perfectly fine. That's perfectly fine. That's very normal. Yeah. Actually, in fact, you can you show that this will eventually be equals to, let's say not fine. Can you show that this will be 6y squared? Can you see why this is 6y squared? Identical.
Okay. I mean, okay.
Why is it 6y squared? Don't understand. Please explain.
1 plus y squared. Square root 1 plus y squared cancel square root.
Here, when you're trying to show an identity, try to for at least for this topic, try to go from left to right. So what we want to do is to substitute, right? Can you see? They're almost the same.
Yeah.
So if I want to substitute this in, I need to isolate it. So there's an irritating tool over here. I don't want it. So I have to bring over. So wouldn't it be nice if I can just do this instead? Half times dy by dx. Wouldn't this be a good strategy? Make square root 1 plus y squared a subject. So we get half dy dx. Right? Half times dy dx. Then from there you can sub in. So what we end up with is equals to 2y on top, all divided by half dy dx. Times dy dx. Following so far?
Okay.
Dy dx is just an expression. Here when you have times half, maybe I can bring the 2 on top. So we end up with
4y.
4y over dy by dx. Let me just put the brackets here, there, and then I times dy by dx. Anything to cancel away?
dy dx.
Dy dx. Oh, wait, that's wrong. Hold on a second. Did I do something wrongly? Let me see. 3.5 minus half. Get a 2y. Is it not 6y squared? Maybe it's actually just 4y. Sorry. This should just be a 4y. Yeah, I should. Sorry, this should just be a 4y. Wrong question. Apologies. No, it's a 4y. This is. I cannot see what's wrong with this. it should be a 4y. Okay, so that's just an example on how to use implicit differentiation. Ken? So this is the first example. Sorry, let me just rewrite this. This is example 1. When this is example 2. Example 1 is above. This is that was example 1 where square roots were involved. Whenever you have square roots involved, try to, like in this case, what is it? Y equals to square root 100 minus x squared. The strategy is square both sides first before differentiation. So it's just some algebra, Square both sides first before you differentiate. And when you differentiate, you're not going to be using normal differentiation, you'll be using implicit differentiation. Okay, that's the strategy I'm teaching you here. When there's a square root involved in the y, you don't just directly take a dy by dx. Yes, I know for now it may look simple, but once you see more complicated examples, then you will realize that, oh, implicit differentiation is the way to go. This strategy I just described. Okay, square both sides first, then differentiate. Alternatively, over here, actually I didn't square both sides. I kept it as its original form, which already doesn't have square roots. You see, think of it like if I started off with this question, I could have worked it out back into that format, x squared plus y squared equal to 10 squared. Then after that, I differentiate. The idea is to avoid square roots. Because it's very messy. Okay, that's the example 1. Okay. Okay, next example, the main point. Okay, I'm still, it's just still illustrating on avoiding square roots. Okay, next example. Okay, this one is just an extra example. This one is just extra. Let's go for example 4. This example 4, I'm trying to show you that avoid sine inverse, cosine inverse, tangent inverse. So should I introduce this now? Why not? Let's just introduce it. What is the let's say that you have a function y equals to sine inverse of x. Okay, this should be on a separate page. Hold on. Give me a second. Let's say we have y equals sine inverse x. What's dy by dx?
I don't know this.
Don't know this. Very good. If you know, then wow, I'm very scared already. Huh? How come you know? Never teach before. But first you need to understand what's an inverse function now. So let's say that you start off. Okay, you actually already know this. Let's say that you have y equal to x over here. Then let's say you have y equals e power x. Then what is my inverse function? It's y equals to ln x. It will look something like this. What's the key pattern? They are reflections.
Sine x and sine inverse x is reflection.
They are reflections, yes. If you restrict the domain, let me show you. You know what? My art skills are not good. I have software. I'll use software. Let me show you over here. Can you see on Desmos? Y equals to sine x, right? Can you see? Oh, let me change to the normal scale. Let's say I restrict it to negative pi over 2 to oh no, that's not what I want to type. Negative pi over 2 less than or equals to x less than or equals to pi over 2. Can you see that? I have restricted the what I call the domain of a function. What's a domain? Domain is the allowed values of x. Now let's do the same thing, but with sine inverse of x. Inverse of x. Can you see?
Yeah.
Look, there are reflections about y equal to x. Okay. reflections, mirror image. Can see all? Okay, very good. So let me just show the full graph of sine inverse x without the restriction on the domain. So in other words, the whole graph. Oh, sorry. Wait. No, that would not be a function. That's a relation. Yeah. So, okay, never mind. Forget I said that. Okay, so they are just reflections about each other around the y equals x. Can? Then how do you find the derivative? Here's how you do it. You really need implicit differentiation. Let me show my iPad screen first. So you've seen it already just now. What was it? Like this. Oh no, that's not very good. That is not good at all. We just draw a sketch of the sine inverse and sine graph. So it looks like this. It looks like this. And y equal to x is here. Y equals to sine x is this. Oh no, that's a wrong drawing. Sine x looks like this. Then sine inverse looks like this. Maybe I should change the color. Is it clear enough? Okay, I hope it's clear enough. Black color is y equal to sine x. Then the pink color is y equals sine inverse x. The orange color is y equal to x. Okay. They're supposed to intersect each other at one point. In this case, at x equal to 0, y equals to 0. They only intersect at one point. Okay. Yeah, so anyways, that's how the sine inverse graph looks. You can do something similar for cosine inverse and tangent inverse, but I'm not going to go through that today. Let's just focus on sine inverse. How do we find the derivative of this function? How do we do that? Let me just show you. So, let me just make it look a bit nicer. What we need to do is to realize that actually you can always bring the sine inverse over, so you get sine y equals to x, right? Then from there, you can draw a triangle, right angle triangle, angle here being y, 90 degrees here. Sine y is x, which is really just x over 1, correct? Okay so far?
Yeah.
But sine is opposite over hypotenuse, right? Remember Tuahaso? Opposite over hypotenuse. So what if we just call this x and 1 here? It's just a ratio, right? It doesn't matter what is the actual length. As long as the ratio becomes x, then we are good to go. So we call opposite side x, opposite of the y, and hypotenuse we call it 1. Following so far? Then how do you get the remaining adjacent length? Pythagoras. What is it?
X 1 minus x squared.
Yes, 1 minus x squared. Okay, good. So from there, we have sine y equal to x. How do you find the derivative? Very simple. Differentiate. Differentiate sine y, differentiate x. How do you do that? What's the derivative of sine y? What's the derivative of x? Differentiate sine, what do you get?
Get cosine.
Cosine, but what's inside?
Square root 1 minus x squared.
No. Keep it as y. Keep it as y. Keep the same. Keep the same.
Okay.
Yes, it is square root. Wait. No. Yeah, it's not. It's not square root 1 minus x squared. Y is the angle. Y is sine inverse x. So it's actually cos of sine inverse x. But you keep the same. Keep the same. That's chain rule. Okay. So sine of a y, you differentiate the outer sine, you get cosine. Right? Good. Then what do you need to do next after you d outer?
dy.
The inner, which is the derivative of the inner y, which is dy by dx. Okay? Equals to
1.
1. Very good. Then from there, you can make dy by dx the subject, right?
Okay.
What do you get? 1 over?
over cosine y.
So let's take a look at this triangle. What do you think is cosine y?
Cosine y is
Ka.
Huh?
Tuakaso. Tuakaso.
Oh, adjacent over hypotenuse. So just square root 1 minus x squared
Over 1, which is just square root 1 minus x squared. Good. Then from there, you can rewrite this as 1 over square root 1 minus x squared. Ta-dong! This is our formula for the derivative of sine inverse. What was y again? Y is sine inverse of x over here. So that means that dy by dx is really just d by dx of y. But what is y? Y is sine inverse of x, which is equal to 1 over square root 1 minus x squared. Whoa. What? What's going on? You can only understand this after you understand implicit differentiation. Okay, so congratulations, you just found a new derivative. Differentiate sine inverse 1 over square root 1 minus x squared. Can?
Okay.
So now let's upgrade this. Let's take this new concept we found. Maybe next lesson then I talk about cosine inverse and tangent inverse, and talk about avoiding it. So after learning it, we try to avoid it as much as we can. Quite funny, yeah. But let me show you. So let's say we start off with y equals to sine inverse of x squared. How do we find dy by dx? Let me demonstrate. So first, you need to realize that there are two functions here. There's an outer function and an inner function. Can you see that? This part is outer, that part is inner. So that means if you want to differentiate, you have to use what rule?
Chain rule.
Chain rule. So differentiate outer function sine inverse. We just figure out our brand new formula here, right? So it's just 1 over square root of 1 minus something square. The something x here is the same as that x there. But is it still a x in this case? In our new question? No. Look, previously was sine inverse of just a normal x. Now it's sine inverse of what? Hello? Sine inverse of x is the old one. The new one is sine inverse of
X squared.
X squared. So that means that previously yellow color x becomes yellow color x power 2. Now we change to blue color x squared. We have to change into blue color x squared as well. X squared. Can you see that? But the power 2 is outside of the blue color highlighter. Can you see the power 2? I highlight in green. Is separate. Can? Yellow change to blue. Or should I just keep it to yellow? Maybe I should keep it to yellow. Can you see what's going on? Can x becomes x squared? Good. But from there, that's only the d outer, right? That's only d outer. How do you d inner now? I hope you remember this is chain rule. We need to d inner as well. Who's my inner function? Who's my inner function?
Where?
So you differentiate the inner function. D inner gives you, what does it give you?
2x.
2x, very good. So you get 2x. Okay, from there you simplify, you get 2x on top over square root 1 minus x power 4 square root. That's how you use the new formula sine inverse. Oh, you're still using the same strategy of d outer times d inner for chain rule, but you realize it's a bit complicated, right? Imagine if this was not x squared, it was something else. It would be even worse. And in the future, you may learn about this topic called Maclaurin series. I don't plan on covering this because it's quite unlikely. Can't say quite unlikely. Actually, quite likely you want to have to learn this in engineering. But by then, you can suffer along together with your fellow intake mates who hasn't studied this yet. So it requires you to deal with much more complicated expressions. So that's when I need to teach you this next example for the strategy, which is to avoid sine inverse. When you start off with a function dy equals sine inverse, you avoid sine inverse. How do you do that? Immediately after teaching you one technique, I teach you how to avoid it because it's very, very ugly. Like, look at this, yuck. So many square roots, minus, bracket, power 2. Wow, so complicated. If only we had something simpler, and indeed I do. So let's try this strategy. What we're going to teach now, what I'm teaching you now is to avoid sine inverse by bringing it over to the other side. Similar to the what I call the proof of the derivative of sine inverse. We start off with sine inverse, which is difficult. So we just avoid the problem altogether by bringing it over to the other side. To start with, so we start with sine y instead. Make sense so far?
Mhm.
Same strategy, we're going to bring the sine inverse over. So what we end up with is sine of y equals to x squared. Differentiate, how? With respect to x. Maybe I slow down a bit. I show you this d by dx, bracket, d by dx, bracket. So differentiate sine y with respect to x. What do you get?
Cosine y
Times,
dy
Cat.
dx
must have a tail, cat tail, dy dx equals to?
2x.
Very good. From there, you can make dy dx a subject. What is it?
2x over cosine y.
Very good. That's it. Done. Okay. But of course, you may think, oh, maybe I need everything in terms of x. So why you replace with sine inverse x squared? And then you get stuck. Oh no. How? What is cosine of sine inverse? I don't know any special trigo identities that can help me. There are identities involving sine inverse and cosine inverse, but most people don't learn it. I also don't know it. Okay, it's available online. I can send you a file later, but it's not important. Most people don't need to know it. What you do need to know instead is this strategy. Look, very important strategy. Over here, sine y equals to x squared. Draw a right angled triangle. What angle do you want over here? Hint. Sine of something, it's always an angle. So what do you want as the angle over here?
Y.
Yes, y. Okay. So read together, sine y equals to x squared. But isn't that just x squared over 1? So sine, do you agree that it's so opposite over hypotenuse?
Mm-hmm.
So who's the opposite? Who's the hypotenuse? In this fraction.
X square.
Then in the diagram, it must be over here, right? X squared, opposite. Opposite of angle y. Then hypotenuse, where is it? The long one or the short one?
Long one.
The long one must be 1. And then from here, you have to do Pythagoras theorem. So let's just call this, I don't know, let's call it L. So L squared plus x squared, oops, sorry, not x squared, must be x squared equals to 1, right? That's just Pythagoras theorem. Correct or not?
Mm-hmm.
That's how you get x power 4. And L squared plus x power 4 equals to 1. From there, L squared equals to 1 minus x power 4. So L equals to square root of 1 minus x power 4. Following so far? We don't need to plus minus because L is a length, positive. Can?
Mm-hmm.
And therefore, I replace my L with square root 1 minus x power 4. Good. And from there, I can figure out what is cosine of y. No, we don't want this. Cosine y will simply be equal to what? What's cosine y?
Will be equal to adjacent square root 1 minus x power 4 over 1.
Which is just square root 1 minus x power 4. right? Therefore, cosine y you can just sub in with square root 1 minus x power 4. So you end up with what? 2x over square root 1 minus x power 4. Ding ding. That's how you get your answer. Same as before. Okay? Okay, good. So usually actually what happens is that you will stop here. You are allowed to stop here. This is good enough. So this part here is depends on whether your prof wants you to do this or not. But usually you can stop here. The pink color one, which we realize is a lot shorter compared to using the explicit way with respect to x. Okay? Okay, that is the example for avoiding sine inverse, cosine inverse, tangent inverse. We'll talk more about cosine inverse and tangent inverse in the next lesson, I guess. I see. Okay, so example 2 was to avoid square roots. 3 is just an extra example. Avoid square root by taking square on both sides. Avoid sine inverse by bringing over to the other side. Now we're gonna avoid more things. Example 5. Avoid multiplications by using logs. Or more specifically, ln. Let me show you. Example. Let's say we have y equals to x squared plus 3x power 5 times, I don't know, let's say x minus 2 power 10. What would you have to do to differentiate this? Product rule, right? Let's say I make your life more difficult now. Sine inverse of x minus 2 power 10. Do you still want to use product rule?
No.
Right? Because end up, this one you try to differentiate, you have to bring down the old power minus 1 to get the new. Okay, that's fine. But now you have to differentiate sine inverse as well. What if I make your life even worse? I make this into x squared. Haha. Do you still want to do product rule? No, okay? That's the main idea. I'm trying to scare you with a crazy example to teach you the new technique. So here is the new technique. Let's say I don't use sine inverse because I'm also a bit scared of it. Let's say we go with sine x. Wow, sine inverse really 1 over square root 1 minus x squared. Wow, that one very painful. Let's just stick with this example. What I want to show you next is, instead of differentiating directly using product rule, avoid product rule. What we want to do is to take a ln. Take ln on both sides. What do I mean by ln on both sides? I mean, this fella here, you can introduce a log base n, log base e, which is called ln, on both sides of the equation like this. Can you see? So let's just leave the left hand side alone. It's just ln y, right? Then ln of this one very special. What happens when you have multiply? On AB equal to what?
ln A plus ln B.
Very good. So over here, you can split it as ln of x squared plus 3x power 5 plus ln of sine x minus 2 to the power of 10. Right? Wow, so complicated. Okay. Then what else can you do? Any other rules you remember from logarithms? ln x power 5. What happens to your power? Is it differentiate? Then 5 ln x and power 4. Is it?
Wow.
Is it? No, that's differentiation. What's the logarithm rule? No.
We can bring down the power.
Yes, you simply bring down the power. ln x power 5, just 5 ln x. Done. Okay? Bring down the power. So here, also got power. Here also got power. What can you do?
Both can bring down.
Very good. Bring it down. Bring it down. So we end up with 5 times ln of x squared plus 3x plus 10 times ln of sine x minus 2. Is that clear so far? Right. Then what you realize is we could change it from a product into something a lot simpler. See, it's just a coefficient times ln. Just a coefficient times ln. Can we differentiate this? Easily? Yes, we can, right?
Really?
Yeah, yes. d by dx on the left, d by dx on the right. Okay. So what's the derivative of ln?
1 over y
1 over the letter. But here, because it is
times
y
dy dx.
by dx tail, to convince you, since you're seeing this first time, let a equals to ln y. What I just asked you to do was to differentiate with respect to x, d by dx of the ln y, right? But I don't want to write this down. Instead, I dA by dx, and I write dA by dx, and I split it up as dA at the top left, dx at the bottom right. And I introduce a dy. So now dA by dy is the same as differentiate ln y with respect to y. In other words, maybe I show this at least one time. D by dy of a. But that's really just d by dy of ln y times dy by dx. Times dy by dx. Differentiate ln y with respect to y is just 1 over y. Then don't forget the dy by dx tail. That's it. Okay? Are you following?
Yeah.
Yeah. So one line, huh? Don't need write so much. Don't need. So long-winded. No need. Shrink it down, toss it aside, put it to the side. You don't need this. You need to see it one time and just do it. Oh, ln y get 1 over y times dy dx. How about this guy? When you differentiate two separate terms, plus in between, you just have to differentiate term by term, right? So let's differentiate this 5 times something. What happens when you have 5 times? Just factor it out. Then d by dx of the ln x squared plus 3x. Likewise for the other guy, 10 times derivative of ln whatever. Copy. 5 times what? Can you differentiate for me?
5 times 1 over x squared plus 3x. Then
That's the d inner. That's the d outer. You still need d inner.
then 2x plus 3.
Very good. See, so simple to differentiate, right? Compared to the other guy, you see, you had to go and use power rule. Wow, take one differentiate other plus take the other differentiate one. So painful. Don't want. Okay, so this is much better. Then plus 10 times of derivative of this ln. What do you get? 1 over sine x minus 2. Okay, times
Sine x.
Huh?
Wait. Yeah, wait. Cosine x. No.
cosine x. Differentiate minus 2. Is it minus 2x?
No.
No, that one is integration. This is differentiation. So it becomes a 0. Okay, good. You didn't fall for the trick. Still awake. Very good. This is the expression. Let's just clean it up a bit. So 5 times 1 times 2x plus 3. That gives me a 5 bracket 2x plus 3. All divided by x squared plus 3x. And then plus 10 times 1 times cosine x, 10 cos x. All over sine x minus 2. Very good. This is 1 over y times of dy by dx. From there, we can stop already. Okay, this is a very good expression for the derivative already. Bing. You can also make dy by dx a subject if you really want to, by simply multiplying y over. And I believe y times this thing, if you really wanted in terms of x, you can substitute the y as well. Okay? Yeah. Y is just this guy. Copy. The final form doesn't matter. It's just as long as the technique used. I mean, as long as the as long as it's an equivalent answer. Yeah. This is just one of the this expression factor out. Okay. And if you actually did it manually using product rule, to get into this format is a lot more difficult. Yeah, so I have to convince you that implicit differentiation is the way to go. Okay? So here is avoid multiplication by using ln. Here is another one. That's last example for the day. Example number 6. We're gonna avoid division of fractions using by cross multiplying. So let's say, for example, we have y equals to x squared over sine x. What would you have to use? Quotient rule, right? So normally you would dy by dx straight away. Then bottom d top differentiate x squared get 2x minus top x squared d bottom, which is cosine x, all divided by bottom square. Low d high, less high d low. Draw the line and square below. Low is sine x, high is x squared. Like this, right?
Faster way.
Is there a faster way? Actually, this one also pretty fast. From this example is simple enough. Should I make your life more difficult? Yes, I should. I need to make your life more difficult. If not, you're not convinced. Let me try a more difficult example. Say y equals to sine inverse of x cubed plus 2x over, I don't know, x plus 1 power 10, x minus 2 power 3. How? Oh no. Wow, this one, low d high, less high d low. Do until you cry at home. Okay. What would you want to do? You cannot take ln yet. What you want to do is to cross multiply. So over here, the denominator, cross over. Okay. So what you end up with is y multiplied by that denominator. So y times x plus 1 power 10, x minus 2 power 3 equals to sine inverse of that guy. Okay. Now, I know what I told you just now. I said sine inverse, you should bring over, right? To make it sine. But here, you have to sometimes check the weigh your different actions, cost and benefit. If you bring the sine over, here's what will happen. Okay, over here, sine inverse travels over to the left, then you end up with just a sine. But now that you have this guy, sine, right, it means you have to take a cosine, differentiate this, and you get cosine of the entire thing, and then times derivative of the inner function, which will be very, very painful because this part here is slow. Right or not? Can you see? So that's when you should do something clever. Ln first. Because what do we have here? Multiplication product. Remember example 5 just now? Yeah. So before you try to bring the sine over, maybe it's a good idea to take a logarithm first. Okay. So actually, I'm just discussing with you techniques to speed up your differentiation techniques. Okay, speed up your differentiation techniques using implicit differentiation. This guy you can differentiate. You know how to differentiate this. With the new sine inverse function that you just learned, 1 over square root 1 minus x squared. It's just that it's very slow. So here I'm teaching you techniques to speed things up. So we're gonna take a ln on both sides first. Have I done any differentiation yet so far in this example? Like in the procedure, I take ln on both sides up to this step. Step 1, step 2. Have I done any differentiation yet?
No.
No, very good. That is the key trick you must remember. You must always do algebra first, then differentiation. If you want to speed up your differentiation, algebra you need to do first. This is just algebra. Take ln on both sides. Cross multiply. Right? Then over here, when you have a product, what can you do? Product change into sum. Ln ABC is actually what? Ln A plus ln B plus ln C. Okay? So it becomes ln Y plus ln of that fellow in the middle plus, sorry, not times, ln of x minus 2 power 3. This one, no choice. Just copy and paste. Can't simplify ln sine inverse. Not that I know of. Is there an identity? I'm not sure. But here, ln of x plus 1 power 10, what can we do with power?
Bring down, bring down, bring down.
Very, very good. So we quickly write that down. Ln y plus 3, not 3, 10. 10 ln x plus 1 plus 3 ln x minus 2. Okay? Equals ln of sine inverse. This one no choice, just copy and paste only. Good. What do we do next? Any other tricks you can do? Before any algebra tricks you can do? We convert product into sum. Please don't go backwards. Please don't go and work backwards. Product need product rule. Very, very irritating. Take one, differentiate other, plus take the other, differentiate one. It's not that we cannot do, it's just that it's very slow. We're trying to avoid that. Okay. I think not much already. Not much. So what we can do next is to differentiate. Okay.
Okay.
So I'll just d by dx on the left side, d by dx on the right side. So when you differentiate multiple separate terms, you can distribute the derivative into each of them, sort of. So you differentiate the first guy, ln y, what do you get? 1 over y. Right? Differentiate ln, you get 1 over. Just as a letter change. But you must always remember, this is y, that one is x, different. So what do you need? Cat must always have a
dy
dx
tail.
dy by dx tail. Very good. Plus 10 times something. So copy down a 10 first. Times differentiate ln. What do you get?
1
One.
over x plus
plus
1.
Then
Then
d the inner. So differentiate x plus 1. What do you get? It's just a 1. 1 plus 0. So you can don't write it. But I'll just leave it there to remind you of the general procedure.
3 over x minus 2.
3 times 1 over x minus 2, which is 3 over x minus 2. Then you have a times 1 because you differentiate the x minus 2. Of course, if you know it's 1, you don't have to write it. Simplify as 3 over x minus 2 straight away. Equals to this one. Ln again, what do you do? 1 over again.
1 over sine.
It's just at this time there are 3 functions, so be careful. How do you deal with how do you use chain rule with multiple different functions inside each other? Just peel off layer by layer. Remember the onion analogy. It's like an onion, 3 layers. Okay, layer 1, layer 2, layer 3. Layer 1 is the outermost layer is ln, so it's 1 over, and everything else you just copy and paste. Okay, after you peel off the outermost layer of an onion, the inside still stay the same, right? So same thing over here. The sine inverse x cubed plus 2x must still stay the same. Does that analogy make sense? Okay, then times. What do you do next?
Times the d inner.
Yes. So who is the inner function this time? We go one layer at a time. Sine inverse. So derivative of sine inverse. Let me just write it down. It's brand new. You might have forgotten it. It's 1 plus x squared. Plus or minus? Let me double check. Sorry, minus. I was wrong. I'm sorry. I don't remember. It's a minus. So differentiate sine inverse, right? What do you get? 1 over square root of 1 minus something square. Okay?
Cube plus 2x.
Very good. Yes. So it's x cubed plus 2x. Let me just write this down. X cubed plus 2x. Okay. And times
square plus 2.
What's missing? A pair of?
Wait. Don't tell me. A pair of brackets.
Yes. Very good. Okay. Then from there, you can make dy by dx a subject over here, and you got your answer. I'll leave you to do it on your own.
Okay.
Now, actually, I don't need you to do that. In the homework question I'll be giving you, it's just on implicit differentiation, and go and then you just have to show me up to this step. Show me that you can do it up to this step, and you are good.
Okay.
Okay. Yeah, then be clever. Be clever. Remember the examples. Avoid division, cross multiply. Then once you have a product going on, take a logarithm. Logarithm will convert a product into a sum, which means that you can differentiate it easily. It also helps you to bring down a power, which means that you can differentiate easily. Can algebra as your first step before differentiation. You see, there's so many lines just dedicated to algebra only. Then differentiation is just one line. Differentiation is just one line. Okay, that's about it. Let me think. Is there enough content you have for homework? Cross multiply identities. Oh, can I just go through one more example? One more example.
Sure.
Can I? Okay. Let me find the right example first. Okay, this one should be good. Okay, so let's write down some of the things you need to know first. This is example number 6. Use identity. No, not 6. 7. 7 already. Use identities to find higher order derivatives. Let me send you the example. Give me a second to send you this. I have just sent you the photo. Can you see it?
I see. Yeah, I see. Prove that y equals sine inverse y equals e to wait, is it e to the power given that y equals e's power to the power of sine inverse x?
Yeah, correct. Is that crazy?
Prove that 1 minus x squared bracket. Okay. Okay.
Hold on a second. My iPad is misbehaving. What is going on? Copy and please paste. Oh, finally, allow paste. And I am back in 3, 2, 1.5, 1, and here I'm back. Okay. Use identities to find higher order derivatives. So part A asks you to prove that you get this identity. Part B, I hid it from you. It's actually on Maclaurin series. So I'm gonna modify it. So from this, I want you to find the y bracket 0, dy by dx bracket 0, and d2y by dx square bracket 0. What does that mean? Bracket 0. It simply means you substitute x equal to 0.
Okay.
How? So find these 3. Let's do with part A first. Let me write down.
Okay,
So let's think about it.
1 y0 is just e.
Yes. E to the power of sine inverse of 0. Sine inverse of 0 is just 0. E power 0 is 1. Hey? No, it's not e. It's
I mean e power 0.
E power 0.
And then okay, dy dx, so chain rule. So keep the same. then E sine power, yeah, okay, then times D inner, which is this one. So we get 1 over times 1 over square root 1 minus x squared.
Yes.
And okay, I mean, can put this on top here, but I mean it's the same thing.
Yeah.
Then d t2y over dx squared is
Ooh.
differentiate this.
Do you realize that this guy has everything that I asked you to avoid? Please avoid square root. Please avoid sine inverse. Please avoid fractions. It has everything in one.
So
what do you think you should do?
Cross multiply.
Let's multiply first. Yes. So what we get is square root 1 minus x squared times dy by dx equals to e power sine inverse. We have yet to do any differentiation. This is just algebra. What do you do next? Sometimes product rule cannot avoid one. How? Here in your first step, you differentiated directly already. So that may not be so advisable. Let me show you another way to do the first derivative. Do a bit of algebra right from the beginning. Y equals e power sine inverse x. You could have just taken ln on both sides straight away. Or actually, e bring over just becomes log base e. So it's ln y equals sine inverse. Then you differentiate with respect to x. So differentiate ln y with respect to x.
1
end up
over
with
y equals
times
dy dx
tail equals to 1 over square root. Then from there, you can make dy dx a subject. 1 over y bring over becomes
y over square root 1 minus x squared.
So you compare with your previous answer. Can you tell why it's a y at the numerator?
Yeah.
Because e sine inverse is actually equals to y. Okay. So this is actually much better to do with. This guy is actually equal to y. So let's just replace this with a y. Then how to find the second derivative?
Ln.
Oh, I never thought about that. You can take the ln. You can take the ln. Okay. Interesting. Let's do that. Ln of square root 1 minus x squared dy by dx. Interesting. Ln y. Can. Then there's a product going on here.
Can split this to plus ln ab equals to ln a plus ln b.
Yes. So ln square root 1 minus x squared plus ln of dy by dx.
Then there's a half here that you can bring down.
Good. So half ln 1 minus x squared plus ln of dy by dx equals ln y. Okay. We haven't done any differentiation yet, right? We want second derivative, right? So
yeah.
What should you do now? Differentiate.
Okay.
Yeah. So let me just save some space by bringing this on top here. I hope it's not too messy. Differentiate this guy with respect to x. Differentiate that guy with respect to x.
Okay.
So half can factor out first. Ln becomes
1 over x 1 minus x squared, then d inner, so times negative 2x. Yeah. Then plus ln dy dx.
Differentiate ln dy by dx.
1 over dy dx.
Yes. 1
Then times
over.
second derivative.
Very good. Yes, you're differentiating the inner, in this case, dy
Mm.
by dx gives you d2y by dx squared.
Equals to 1 over y. Then dy dx.
Yes, correct. Very good.
Then
From there, let's take a look what we need to prove.
I mean,
Actually seems quite complicated.
yeah.
2 cancels away. Let me see. Okay, it's correct already. It's correct already. You just need to do a bit of algebra. So let's take a look over here. d2y by dx squared, what's the coefficient?
Oh, 1 minus x squared. I mean, there's
Is
a
there a
1 minus.
fraction? Is there a fraction? Or is it just over 1?
It's just over 1.
Just over 1. So look at this guy, d2y by dx squared. Is there a fraction? Or is it just over 1? Currently, there is a fraction as a denominator, sorry, dy by dx.
Times
So we don't want that then.
everything
By
times everything by dy over dx, and then
Yeah.
times everything by 1 minus x squared.
very good, because there is no 1 minus x squared denominator over here. Okay, so let's do that. Whew, this is gonna be 1 minus x squared times dy by dx. Let's think carefully. So this first fella is negative x over 1 minus x squared, multiply 1 minus x squared, multiply dy dx. 1 minus x squared cancel away, left with minus x times dy by dx. Okay, plus next one. This second term, you times dy by dx to cancel away, times 1 minus x squared just goes to numerator. Left with 1 minus x squared times d2y by dx squared. Starting to see the pattern?
Yeah.
Very good. Then the next one, 1 over y times dy by dx. Okay, no choice, copy first. But you multiply it by what was that fellow? 1 minus x squared times dy dx. Let's just copy and paste this. 1 minus x squared dy dx. If I can just look at this. Okay, you know what? Let's make it look nice. I'll also use red color here. Can? So you start to see the pattern already. Minus x dy dx, okay. Plus 1 minus x squared dy dx squared, okay. But here you need minus y equals 0. Here you don't have a 0. So what should you do?
Sub this in.
Sub in first. Okay, can. Then okay. Let me see. Let me see. Sub this in, is it? Let me think a bit. Let me think a bit. Hold on. Because what we really need right now, you see that this term is the same as this term. That term is the same as that term, right? So we are 66% there already. 33. We're left with a minus y equals 0. So here the only difference is this part here. So how about we do the following first before we continue? We take this left hand side. We take that guy on the right hand side, bring over to the left side. So we put a minus equals 0. Okay, so our end goal now is really just what? It's really just to show that this fella here and that fella there are the same.
Yeah.
Okay. Let's see. I have to be very careful now because we are very close. If we make a wrong move, we may end up going down a rabbit or go down a path that is totally wrong. So you have to be careful. If you sub in y with this guy, what will you get? Let's just do it first. Let's just do it first. Put it at the side. If you decide to sub in the dy by dx with that fellow, okay, let's make this disappear. Then the question is, how come the other guy dy dx you don't want to sub in as well? Or should we do it as well? Look, remember the angle? We need minus y. Does that guy have any dy dx at all?
Yeah.
No. The angle, our objective.
Oh no.
Minus y. Here don't have, but here we got 2 copies of dy dx. So that's not one. What should we do? Sub in for both of them.
Okay.
Don't just sub in for one, sub in for both. Okay. Let's do that. So 1 over y times dy dx, remove the dy dx, replace it with this fellow. Is it okay? Let's see if anything cancels away. Oh, I see one thing. Y and y cancels away. Then let's simplify this.
Okay, got a 2 over 1 minus x squared. This doesn't this and this cancel?
Yes, it does. So let me just
And
make it more convincing. 1 minus x squared on top over square root 1 minus x squared, square root 1 minus x squared, and then you times y. Square root times square root is power half times power half. The base is the same, so you can add them together. It becomes 1 minus x squared power 1 over 1 minus x squared. And then, yes, they cancel away. You're left with a y. Yay, we are done. Get our y. Okay. But don't forget our minus sign, minus sign, minus sign, minus sign. And therefore, this is minus y equals 0. Everything else copy and paste. But just to make sure we show the proof question, we swap the order around, just to make sure it looks exactly the same. And then we're done. Okay.
what's the normal way if you don't do by ln?
Oh, if you don't do by ln, right? Usually what I would be doing is just use product rule already. Just use product rule. Yeah.
All right.
Yeah. I never thought of this, taking ln. I never tried to follow my own advice before. Ln of dy by dx, very, very interesting. Interesting. You can still do it 1 over dy dx and differentiate that, Yeah, that works. Why not? Okay. But that is only for part A proof. Now you have to do part B. Find y of 0. Okay, that's done. It's over there. Find dy by dx, sub in x with 0. Find d2y dx squared, sub in x with 0. How? So let's summarize what we know. X equals 0, y equals 0. What else do we know? We know expression for dy by dx. It's over here. So if we want x equals to 0, what is dy by dx bracket x equal to 0? This will simply be that expression, but you replace the y there with what? 0, right? Because it was previously a y. So when x equal to 0, y is 0. So you can replace that y with a 0. And 0 divided by anything is really just equal to 0. You don't even need to sub the x. But if you really wanted to, it will become 1 minus 0 squared. 1 minus 0 squared, that's just 1. Square root 1 is just 1. So it's 0 over 1, which is 0. Okay? How about if x equals to 0, what is dy by dx? D2y by dx squared. So we have to use the expression above there. Okay, even if you couldn't show part A, you can use part A. Sub in with x equal to 0, what do you get? Just sub in. So this is a bit difficult, right? Draw a question mark first. Instead, you go from here, you sub in x equal to 0 first. So 1 minus 0 squared is 0, bracket, times d2y by dx squared, minus way 0, let me use red color, 0, times of dy by dx, minus away y happens to be 0, equals 0. Okay?
Why you cannot sub dy dx is 0?
Oh, sorry, I forgot. Yes, you can do that too. Right, correct. This guy can also be sub in. Because I already know by then 0 times anything is just 0. So
it doesn't matter.
No point. It doesn't matter anymore. Yeah. So anyways, 1 minus 0 gets a 1. 1 times anything, might as well not write it. It's just d2y by dx squared. Minus away 0, minus 0 equals 0. D2y by dx squared is still equal to 0. Okay, everything is equal to 0. Okay?
Wait, this one, like you can just it's because when x equals 0 and y equals 0, so you can just sub in both.
Yes, you can.
Okay.
Yeah, because it's under the same condition that x equal to 0. If it's under x equal to 1, then it's not related anymore. Okay, that's it. That's all the examples I have. I'll send you homework, then you can go and practice. That's all.
Okay.
Bye bye.
Alright, thanks.
And thank you. Thank you. Bye bye.
Bye bye. Pray for my wisdom tooth tomorrow.